quantum model of the atom, and that's kind of what we know today about the atomic model, what it kind of looks like. We talked about these orbital shapes and all that kind of stuff. That's kind of what we know today. But we're going to focus on what's called the quantum number for an electron. Okay, giving an electron what's called a quantum number. And a quantum number specifies the properties of the atomic orbitals and the properties of electrons in the orbitals. So essentially what the quantum number does is it gives us an address for our electron. That's really important. The quantum number gives us an address for our electron. So in your street address, how many different parts of the address are there? House number, street name, city, state, and zip code, right? There's 4 different parts to a street address. There are also 4 parts to a quantum number. 4 parts to the address to the electron as well. So we're going to go through what are those 4 parts and what does it look like, okay? The first part describes the energy level of the electron. So it tells us, is it in the first energy level, the second, third, all the way through 7? There are 7 energy levels total because if you look on your periodic table, there are 7 periods or 7 levels. 1, 2, 3, 4, 5, 6, 7. Right? They can go all the way 1 to 7. The second one tells us the shape of the orbital that's in. Is this electron in an s orbital, a p orbital, and then do you remember what the other 2 types of orbitals are? S, p, what's the next one? D, and then F, right? Those are 4 different shapes of our orbitals. We're going to go over these with more detail in just a second, but this is kind of an overview. Third, it tells us the orientation or the version of the orbital that electron is in. Okay, it tells us the orientation or the version of the orbital that it's in. So let's remember this real quick here. In the p orbitals, how many versions of p orbitals are there? We can hold 6. Each one holds 2. So there are 3 versions of the p orbital. That's why we draw 3 lines when we do orbital notation, right? How many versions of the d orbitals are there? 5, right? Because I draw 5 lines. We've looked at that. And then for f orbitals, there would be 7 different versions. So we'll walk through how do we figure out what version of the orbital it's in. And then the last part of the quantum number describes the spin state of the electron. So is it the one that's spinning positively or the upward arrow, or is it the one that's spinning negatively or the downward arrow? Okay, so remember that quantum number has 4 parts. I would highlight that, circle that, do what you need to do. 4 parts to the quantum number, because a lot of times I'll say, what's the quantum number of sulfur? And you say 8. Nope. Okay, nope. Quantum number has 4 parts. It's a full address. Okay, it's got to have all 4 parts to it. And so I'll show you how do we list it. What do the parts mean? Okay, so let's start with the first part of our quantum number is given with an N. Okay, let me give you an overview of how a quantum number is written. If I would ask for a quantum number, it would look like this. Oops. N, L, M, MS, right? There'd be 4 different numbers, and those numbers are given by variables, okay? But there would be 4 numbers. So it might be 1, 1, 0, -1, half, okay? That might be what the quantum number is, but it's 4 numbers in parentheses separated with commas. That's essentially what a quantum number looks like. And so the first part of our quantum number is given with an N, okay? And that N, all that it represents is the principal energy level or the main energy level of the electron. So if my electron was found for example, in the 1s orbital, my principal energy level would just be 1, right? Because it's found in the 1s orbital. Okay, so my first part of my quantum number would just be 1. If my electron was found in the 3d orbitals, what would my principal energy level be? 3, right there. Right? It just comes right from our chart, okay, or right from your orbital notation. Okay, values of that first part of our quantum number cannot be 0, and they cannot be greater than 7, right? It just has to be a positive integer 1 through 7, depending on what energy level it's in. Okay? All right, second one is given by an L, okay, or a cursive L, kind of is how it's represented, and it tells us what shape of the orbital is that electron located in. And each shape of the orbital has a different numerical value that it's partnered with, essentially, okay? Those values can be 0 to 3, But the way we know what the number value is from this table right here. Okay? So it tells us, this is supposed to be the L right there. If my electron is in an s orbital, the part of the address or the number that goes with the s orbital is 0. If it's in a p orbital, it's number 1. D is 2 and 3 is f. So I like to just remember it with my hand, right? I just go S, P, D, F, right? S is 0, P, D, and F. That's the only kind of just a quick way for you to remember that, right? S is a 0, P, D, and F. Okay, so let's walk through a quick example so far. Let's say that I wanted the address for an electron that is in the 2p orbitals. Let's just say, for example, my electron was in the 2p orbitals. My quantum number would start out how? What would be the first part? 2. The second part of my quantum number tells me the shape. So what would be the next number that comes in my quantum number? 1, right? And then I would go from there to complete the other parts of it. Are we on the same page so far? Right? 2p is 2, and then the p orbital shape is represented with the number 1. Okay, so what if I said that my electron was in a 3d orbital? Well, how would my quantum number start? 3, 2. Right? And I don't know how to do the rest of it just yet, but I would start with 3 and then a 2. Questions with that? Okay. The third one is symbolized just by an M, and it tells us the version of the orbital that it's in. Okay, the version of the orbital. So what version of that p orbital, what version of the d orbital, blah, 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 blah. Okay, values of M are whole numbers, including 0 from negative L to positive L. And so that is a little bit tricky to think about in its whole term here, but here's what I'll show you. We're going to do an example of this, but it comes from an element's orbital notation. That's how we can identify what the numbers could include. Okay, so let's do an example so far. I want to pick an element. I want to pick oxygen. So let's do an example with oxygen. So far, the 3 numbers that we can find. But we start by drawing oxygen's orbital notation. And I really only need to draw the last part of oxygen's orbital notation. And so where is oxygen's last electron found? 2p4. So here's how oxygen is 2p4. And so I would draw out the orbital notation for 2p. Right? 2p1, 2, 3, and 4. Right? So the electron I'm focusing my energy on is this one. It's always the last one to go in. Does that kind of make sense how I figured that out? Right? Oxygen is 2p4. So I went 1, 2, 3, 4. And then I circle it to kind of give me a focus on what electron am I trying to give the address for. Right? When we do an element, we're always talking about the last electron that goes in. So if I was going to start the quantum number for oxygen, the last electron in oxygen, its principal energy level is what? 2. The shape of the orbital is p. So S, P, right? That's where it gets a 1. And then we have to tell the version of the orbital that's in. So essentially we're looking at which of these lines does it fall on, right? Which version of the orbital? And so to figure that out, we're going to label those orbitals. Let's look at this. It says values of M could range from negative L to positive L. So in our case, they could range from negative 1 to positive 1, right? Because my second value is 1. It can range from negative 1 to positive 1. So here's how we know that. We start with the middle and we label that orbital with a 0. And then we label positive 1, negative 1. We kind of think of those orbitals as a number line. Right? The center orbital gets a 0. And then this is the one version of the orbital. This is the other version of the orbital.
Would it be the same for like 5p4?
5p4. Yeah, every p orbital gets labeled 0, 1, negative 1. Yep, good. Okay, so now if I'm going to tell what version of the p orbital does this electron fall on, what do I get? Negative 1, right? So that's the third part of my quantum number. We draw out the orbital notation and we figure out what version of the orbital does that electron fall on. Okay? Yeah.
What about for like D?
Okay, so if we had a d orbital, let's just do an example of one that looks like that. So I'm going to pause that sample for a second. Give me an atom that's in the d orbital. Titanium. Okay, so titanium ends in 3d2. Would we agree? 3d2. So I'm going to draw out my d orbitals. 1, 2, 3, 4, 5. And here's my 2 electrons. 1, 2. All right, so I'm focused on that electron right there. If I was going to start my quantum number, it would be 3. Then what number does a d orbital get?
2.
SPD, right? So it gets a 2. And then if I'm talking about what version of the d orbital it falls on, I start with 0, 1, 2, -1, -2. So the version of the orbital that it falls on would be -1. Do you see how that works? For every type of orbital, when we start to label the versions of the orbital, we start with 0, and we just work our way out, right? And we said this value can range from -2 to +2. -2 to +2, right? It doesn't have to be on the ends, but it falls within that range. Okay, are we feeling okay so far about how we get those first 3? The last one's the easiest one. Okay, the last part of the quantum number only has 2 options for what it can be. It's the spin state. +1/2 or -1/2. The +1/2 is just the arrow that goes in first, the electron that goes in first. It's going to be the positive one. The second one is going to be the negative one. That's the one that's pointing downward, right? It's the electron that gets placed second in the orbital. Okay? So the only 2 possible values for the 4th part of our quantum number are +1/2 or -1/2. Okay, +1/2 or -1/2. That's the only 2 options. So I know this seems like a lot, right? I just threw at you and all of these numbers and where do they go, right? But if we can start from orbital notation, drawing out those arrows, I do think it's a little simpler. Okay? So let's go back and finish titanium real quick. All right, titanium we said was 3d2 and we had it drawn out to look like that. This is a 3d orbital. 0, 1, 2, -1, -2. We said that the quantum number started like this. 3, 2, -1. And then what would be the spin state for this electron? +1/2 or -1/2? +1/2. It's pointing upward, number 1. But it's the first electron to go in this version of the orbital. So it would be a +1/2. So that would be a completed quantum number right there. Right? That's a finished quantum number. It's got all 4 of our parts. 1, 2, 3, and 4.
So if the arrow's pointing up, it'll be positive.
Yep. And if the arrow's pointing down, it would be negative. Okay? Let's try a couple of these examples. Well, I don't know. We might only get through one here, but find the quantum number for the last electron placed in arsenic. And so when it says the last electron placed in arsenic, that's what we've been doing. But that just means for arsenic, we're studying electron number 33, the very last one to go in. Okay? So if I look at arsenic is AS. How does its electron configuration end? 4p3, right? So I like to go ahead and draw out those p orbitals, 4p. And I've got 3 electrons that need to go in. 1, 2, 3. So now do you understand why it's so important to put them in the correct order? Right? Because if we don't, we would have the wrong version of the orbital. We might have the wrong spin state, right? It's got to go in 1, 2, 3 rather than 1, 2, 3. Okay, so which electron are we studying here?
The last one.
Right there. Okay, so let's start our quantum number. We know that the first part of our quantum number is the energy level. So what number? 4, right? It comes right from there. 4. The second part of our quantum number tells us the shape. Good. So what number, what numerical value goes with the p orbital? 1, right? S, P, D, F. So it's a 1. Then we've got to tell what version of the p orbital. So we label them 0, 1, -1. And so what value is our quantum number going to get here? A positive 1, because the electron we're studying is on the version of the orbital that is positive 1. Last part of our quantum number here. Is it the positive 1/2 or negative 1/2?
Positive.
Positive 1/2.